So we've seen in the simulations, in the two-dimensional simulations, that in homogeneous medium where we actually expect physically an isotropic, spherically symmetric wavefront, sometimes this is not what we see. Sometimes we see so-called anisotropic behavior. And I promise we'll look whether we can actually understand that from an analytical point of view. And again, we resort to the so-called von Neumann analysis, trying to develop an analytic understanding using a plane wave trial solution. So in 2 dimensions, a continuous plane wave is given like that. You have P of x, z, t is equal to e to the I kx minus omega t. And you see here k and x in boldface. So these are both vectors. K is the wave number vector. I explain that in a second. And x is actually the position vector. So that's a vector product. And if you write it out, it's actually kxx plus kz, z. Now, what is the wave number vector k? K, it has components kx, and kz is actually a vector that points in the direction of propagation, and basically is a vector that's constant on the plane of constant phase. With this, actually, we now can go again into the wave equation and try to solve this analytically. But before we need again the discretization, so we move into the discrete world, because x will be j dx and z will be k dz. Again, we assume for simplicity that space is discretized with the same space increment in both directions, so dz equals dx. And we can replace it dz basically by dx. So with this discrete representation of a plane harmonic wave in 2 dimensions, we now enter the wave equation, and we go through the whole algebra as we did in the 1-dimensional case, which I spare you at this point, but I invite you to actually try this out. We will see this later in the exercises, and I will show the result. Remember that this allowed us basically to determine the velocity c as a function of wave number, and now we can actually look at the velocity, the physical velocity, as a function of propagation direction. The vector k we can also formulate as with components with the modulus of k multiplying cosine alpha, where alpha is the angle to the x-axis, and kz, which would be the modulus of k times sine alpha. So basically that allows us to actually calculate the error of the velocity, the physical velocity, as a function of propagation direction alpha from 0 to 360 degrees. And the results you see here in this graph, and it shows exactly what we've seen in our simulations. And it's very interesting that you notice that the most accurate direction of propagation is actually 45 degrees to the coordinate axis. That's not necessarily intuitive, but that is the case. And the least accurate directions are actually the directions along the coordinate axis, in that case plus x, plus z, and minus z. So in conclusion, we say we understand that behavior of numerical anisotropy that we've seen in the simulations in our Python implementation. It can be nicely derived here for the scalar acoustic wave equation with the so-called von Neumann analysis. And of course, it's very important to avoid this kind of behavior, because sometimes, for example, you want to understand physical anisotropy that exists in the Earth, for example. By all means, you would not want to confuse that with numerical anisotropy. So it's very important again, as in the 1D case, to have enough number of grid points per wavelength to be so accurate as to avoid this effect of numerical anisotropy.